Hello everyone. In this lecture, I will discuss the nuclear fission process from the point of view of two aspects. One is the extension of periodic table. That means essentially synthesis of heavy elements. So I will not give too much details, but explain the concepts behind what are the limitations in extension of periodic table, because that also involves a nuclear fusion process. And second is what are the research or what is the work going on producing electricity from nuclear fusion process. Okay, so first let us discuss the extension of periodic table. You know that the elements up to 92 were available till 1930s, and after the discovery of nuclear fission, the attempts were made to synthesize heavier elements in neptunium, plutonium by N-gamma reaction followed by beta-minus decay, and with the accelerators producing heavy ions, charged particles. Then by fusion reaction also heavy elements were being synthesized. And by this time elements up to 118 have been discovered. Majority of them, in fact beyond element 100, most of the elements have been synthesized by nuclear fusion of heavy projectiles with the heavy targets. And so, but there is a limitation. There are some inherent limitations in extending the periodic table that I try to explain in this particular presentation. So the limitation due to fission, as I discussed in the previous module, that facility parameter. If you have a facility parameter 0.6, that will correspond to a mass number of around 100 or so. You can see from here z square upon 50.13 into A, you can calculate. So these nuclei are almost, they are stable towards fission. They will not undergo fission. Whereas if you see x equal to 0.8, so this comes to around californium or einsteinium, fermium, z equal to close to 100. And these nuclei will have the fission barrier of the order of even around close to 1 MeV or so. So the fission, so this is the spontaneous fission happening. They are having very short half-lives, so because they have a high fission probability. But if the facility parameter is 1, then there is no fission barrier. You can see here, there is no fission barrier for this nucleus. And so you cannot produce these nuclei. The moment they are formed, they will undergo fission. For them, the fission barrier is 0. So that is the limitation. Because of this instability towards fission of these heavy nuclei, it is very difficult to extend the periodic table. Another aspect, so the fission barrier decreases with the increasing atomic number, and you can see how the facility parameter is changing for different nuclei. You can calculate from here. So let us say z square upon 50 into, let us say 200 mass number. So let us take 100 square upon 2, so it will become 10,000. So 10, that means 10,000 upon 10,000, that is equal to 1. So a nucleus of mass number 200 will have 1 facility, so it will not survive. But if you make it 250, so it will become 125,000. So if you put 12,500, then it will be close to 0.8. The facility will be close to 0.8, and so it will have some finite fission barrier, and therefore it can survive fission. Another aspect is the angular momentum. Angular momentum is adding to disruption of the nucleus, like Coulombic repulsion. The Coulombic repulsion is trying to separate the protons away, and that is the negative, that is the factor which accelerates fission. Another thing is angular momentum. So in a heavy ion reaction, When you bring in a heavy ion, it will bring in angular momentum, and the angular momentum will try to destabilize the nucleus. So because of that, there is one more term apart from surface energy. So if you recall the expression, if you recall this one, for surface energy, Coulomb energy, the angular momentum term also will be destabilizing the nucleus. So the net result of surface energy, centrifugal energy and the Coulomb energy will dictate the fission barrier. And so because of this, for the same nucleus, if you have higher angular momentum, fission barrier will decrease. What I am showing here is you increase the angular momentum from 0 to 20, 40, 60, 80 H cross. For this nucleus 153 terbium, the fission barrier for zero spin was around, this is 35 or so, 35 MeV, and it is going down to close to, let us say, 5 MeV at angular momentum of 70 or so. So you can see sharply declining fission barrier with increasing angular momentum. So in heavy ion reactions, invariably you will have higher angular momentum, and so they will be more unstable towards fission. What I have shown here is the profile, locus of the number, angular momentum and mass number for nuclei having fission barrier 0. The angular momentum for which fission barrier becomes 0, we can see here for a mass number around 150, it can accommodate about 90 H cross of angular momentum. But for a nucleus of mass 300, it cannot accommodate even 5 H cross. So that means what? The fission barrier for the angular momentum for which fission barrier becomes 0, it is increasing and then it becoming decreasing. So when you go to heavier elements close to 300, they will have nearly 0 fission barrier. So that's why you will find that their survival become very difficult, and so it is that puts a limit on extending the periodicity. The third is the competition with particle evaporation limits the formation of heavy nuclei. So fission competes with the particle evaporation, and therefore that puts a limitation on the survival of the heavy nuclei. So there are different ways to reduce the particle evaporation by using what we call it the cold fusion. That means you produce a compound nucleus which have very low excitation energy. So there are different ways, but we will not go into details of those processes. I just wanted to give you a feel that what are the limitations in extending the periodicity. Another thing is to hindrance to fusion. There are other limitations that when two nuclei come together, then there are other factors which hinder fusion of nuclei. So if you recall the previous lecture, I have shown in the compound nucleus mechanism that suppose a nucleus is coming close to another nucleus, Z1, Z2. So this is the R versus the potential, and this is nuclear potential is like this, the Coulomb potential is like this, and the sum total of that will be, so this is the fusion barrier. Once you bring in angular momentum, then angular momentum also is a repulsive barrier, and so that will reduce the pocket. So the fission barrier will decrease, and a time will come for higher angular momentum, this pocket, there is a pocket being formed in fusion, a pocket will vanish. This is what I have tried to show here, that for argon plus 197 gold, the nuclear potential and the Coulomb potential will give rise to this pocket. This is a pocket in the fusion barrier. For heavier projectile like xenon plus gold, target is same, but the projectile is now increased. You will see here that the Coulomb barrier is here, nuclear potential is here, and the fusion profile has become very shallow. That means this pocket starts vanishing, and once this pocket starts vanishing, the compound nucleus formation becomes difficult. So the two nuclei cannot come close enough to fuse and form a mononucleus called compound nucleus. So you can see here 54 plus 79. If you want to go to heavier elements, you have to have heavier projectiles trying to fuse with the. So the nuclear physics community is trying to study what are the factors that will limit the formation of heavier elements. So there is a effective facility parameter they call J square by A effective. They say that if it is less than 48, so again it is nothing but it's like a Coulombic energy of a dinuclear system. If it is less than 48, then you may be having a pocket. If it is more than 48, then you may not have the pocket. So you can see here for argon plus gold it is 31, for xenon plus gold it is 52. So that is how this is one of the limitations in fusion of projectile and target to achieve synthesis of heavier elements. So the nuclear chemistry fraternity has been engaged in synthesizing heavier elements. There are predictions based on cell model calculations that nuclei having atomic number 114 and neutron 184 are expected to have long half-lives, and that is what is called super heavy elements. These super heavy elements around this region may have a long half-life. So people have tried to in fact separate them from the natural resources, from the Earth's crust, wherever there is a large deposits of uranium, thorium, people have tried to separate some elements resembling their lighter homologs, but so far there has been no success. In the process, people have been trying to synthesize them by fusion reactions. So as I was mentioning, the hot fusion, you take lighter projectile and heavier target nuclei, or cold fusion, you take heavier projectile and not so heavier targets. So by cold fusion reaction, you try to produce a compound nucleus which is not very hot in terms of excitation energy. And so by these processes, people have tried to synthesize heavy elements, and because of that, the half-lives are very long, very short, but still attempts are going on to synthesize heavier elements. So you can see here, the periodic table has been extended to mass 118, and these experiments take a very, very long time. In fact, even to synthesize elements, these elements, Rutherfordium, Dubnium, Seaborgium, which the chemistry had been also studied, element 104, 5 and 6, lot of chemistry has been studied. Even there, the production rates are 1 atom per hour or so. As you go to higher and higher, like this highest elements, production rate may be 1 atom per month or so. You can see here the kind of experiments people are doing, and then they have to get an unambiguous signature of that it is that Z and A. So the atomic number, the mass number of that particular isotope has to be established to claim that they have discovered their new element. So what they do actually, when this heavy element isotope is produced, they will undergo alpha decay, and the alpha decay energies are monitored. For the lighter part, lower daughter products, the alpha decay energies are known, and so that is how they correlate that this daughter is growing from this parent. So this is the atomic number and mass number of this particular heavy isotope. So element up to 118. So the super heavy element, as we are calling, N equal to 114, Z equal to 114, N equal to 184, is close to that region the people have achieved, but the half-lives are not long enough. Half-lives are very short. They are in millisecond, microsecond range. So still people are maybe searching for the super heavy elements with long half-life, but the experiments in accelerators to synthesize elements beyond 180, that is 119, they are now going on. They are planned in Japan and USA. Now, in fact, the different countries actually are pooling their resources to plan such mega experiments to synthesize heavy elements. So, to conclude the part of nuclear fusion in producing heavy elements, I would like to say that there are experiments going on using nuclear fusion reactions, wherein you try to understand what are the factors that limit the extension of periodic table. People have tried to produce heavy nuclei by hot fusion reaction or cold fusion reaction, This cold fusion is not the type of cold fusion which were in between it came in the news, that the fusion of hydrogen isotopes to give neutron. This is a fusion of heavy nuclei, but to give lower excitation energy to compound nucleus. So you want to survive the fission, so you produce compound nucleus with low excitation energy so that it can survive fission. Now I will come to the next part, how to produce power from nuclear fusion and what is the status as of now. So the fusion of two light nuclei to form a heavy nucleus to release large amount of energy is similar to fission process, and fission process has been already realized to produce electricity because we can control the reactor very easily. But in the case of nuclear fusion process, that still is yet to become a reality. So let us discuss this nuclear fusion, the fusion of lighter isotopes. So here we have the different types of nuclear fusion reactions. Fusion of deuterium plus deuterium giving rise to helium-3 and neutron. The Q value is 3.2 MeV. Fusion of deuterium and tritium to give rise to helium plus neutron. Q value is 17.6 MeV. And fusion of lithium with hydrogen to give rise to helium-3 and helium-4. Q value is 4 MeV. Now, as you know that these are all charged particles. So if you want to fuse the charged particles, you need to cross the Coulomb barrier. And so there are different channels which people are trying to explore for achieving a nuclear fusion process which you can sustain. I will discuss very soon what are the problems in sustaining a fusion reaction. So this is a simple deuterium plus deuterium giving rise to helium-3 plus neutron 3.2. Like that you will have deuterium plus tritium. So let us see what are the problems in excitation, in achieving a fusion reaction. So as I was mentioning, these reactions, different fusion reactions of lighter isotopes of hydrogen, the one which is having deuterium plus tritium having the lowest threshold, that means the Coulomb barrier. So in Coulomb barrier you know already, Z1 Z2 E square upon R1 plus R2. So for deuterium plus tritium, the Coulomb barrier in terms of kilo electron volt or so, that is having about 10 keV. So the Coulomb barrier for this will be 10 keV, and if you translate this 10 keV into temperature, it becomes 10 to the power 8 degree Kelvin. So if you want to, it's like a threshold reaction, threshold energy. So if you want to induce fusion of deuterium and tritium, you require to achieve a temperature of 10 to the power 8 Kelvin. Now you can imagine, unlike in the case of neutron-induced fission, you didn't have this problem because thermal neutron can induce fission. But for charged particles, you require to have very high temperatures, and then if you have to achieve high temperature, what kind of container you will have to hold these reactants at such a high temperature. So the storage materials, storage vessels, how to achieve at this temperature, matter will be in the form of a plasma. So you have to contain the plasma in a container. So all these are the limitations for achieving a fusion reaction. So now there have been attempts going on for last many years, several decades have been spent, and there are mainly two types of approach people have followed. One is the inertial confinement. So what is that you are trying to confine? That deuterium tritium plasma. The deuterium tritium they have to fuse together, and you require a temperature of 10 to the power 8 degree Kelvin. So how do you contain this plasma? So the one approach is called inertial confinement. By inertial confinement you mean that by virtue of their mass you confine the solid fuel in a very small volume, but you have to also have a high temperature. So you achieve high temperature by bombarding them with high power laser beams, CO2 or NdR laser beams, and you take a solidified fuel. So when the laser beams bombard on the solidified fuel, it will ablate the surface atoms outside, and these ablating atoms will give a recoil to the core, and the density will increase. So you contain the core of the solidified fuel by ablating the surface atoms using a laser beam. So the evaporating atoms on the surface bring together the interior atoms by the recoil of the ablating atoms, and that will lead to rise in the density of the core. And in the process, when the density is rising, temperatures can go beyond 10⁸ Kelvin, but then it may not sustain for a long time. So there is in fact a Lawson's criterion, which I will discuss very shortly. So for a very short time, you can achieve very high temperature, but during that time, the fusion can take place. So in the process of inertial confinement, the reacting particles like deuterium and tritium are held together by virtue of their mass, and that is why it's called as the inertial confinement. So this inertial confinement, by using the laser beams to ablate the outer surface layer to increase the density of the core, is experiments are going on, but it has not been that successful as the next experiment of magnetic confinement. In the magnetic confinement, again you take the deuterium tritium fuel in the shape of a donut, like a tire, and that you have it the tire in the central portion of this tire, the plasma can rotate, move, and how do you confine, how do you avoid the plasma touching the container walls using the electric and magnetic fields. That is in fact that is called as the tokamak system, where the electric field will accelerate the particles, it will increase the kinetic energy of the reacting particles, and the magnetic field will keep the fuel away from the surface. So you have to adjust the electric field and the magnetic field to have the plasma, and when they are fusing, they should not touch the container walls. So the magnetic confinement strategy has been working, and there have been several attempts to generate the tokamak type of reactor worldwide. One of the conditions to sustain a fusion reactor is called the Lawson's criterion. The Lawson's criterion essentially emphasizes how to achieve a plasma density upon beyond certain number for a reasonably long confinement time. So we have to confine the plasma for a reasonable length of time. So this criterion is rho tau. Rho is the plasma density and tau is the confinement time. So if you have to have higher energy output than the energy input is being given to heat the plasma to a temperature 10⁸ Kelvin. If the product of plasma density and confinement time is more than 10⁻14 second per cc for the deuterium tritium. For deuterium we 10⁻16 second per cc. So for this is the one which have a lower threshold. So the lowest temperatures required for this fusion reaction. So this is the confinement. So if you have a high plasma, you will find high plasma density, then slightly lower temperatures or lower confinement time also will do. So overall attempt is to increase the confinement time and the plasma density. So these are the two efforts are being made to have Lawson's criterion. If you can have a high plasma density and high confinement time, nothing like that. So let me see what is the current status in the form of for producing electricity from fusion reactor. Since this is a very, very costly affair to have to build a reactor which you still do not know when it will work, so there has been an international effort called ITER, International Thermonuclear Experimental Reactor, which is most of the majority of the countries which have interest in this fusion energy have come together, and they have proposed a fusion reactor at Cadarache, France, south of France. So this is the world's largest experimental tokamak fusion reactor which is being proposed. It is funded by European Union largely, and India, China, Russia, Japan, South Korea and USA contributing 9% each. So every country, whoever has a stake in the fusion power, they want to contribute this, and this construction of this fusion reactor began in 2007, This is 2022, so already 15 years have passed, and the first plasma from this fusion reactor is expected to be produced by 2025. In fact, India has contributed a great deal in cash and kind. In fact, the cryostat for this reactor was built in our country, and many universities in the country are also participating. We have an Institute of Plasma Research at Ahmedabad, Gandhinagar. They are the leading agency in the country to contribute in the plasma research and the fusion reactor. So this fusion reactor based on deuterium-tritium fusion is expected to start operation by 2035, and this reactor is expected to have a power of 500 megawatt, which will be sustained up to 1000 seconds. So you can see here that even this is a very meager target, because what do you do for after 1000 seconds? So but this is such a challenge. It's a really big challenge. So this kind of mega projects, if you can sustain, if the such a high power of fusion power for 1000 seconds, it will open up gates for the sustaining to actually realizing the fusion, electricity from the fusion in the times to come. So this is the one area where there is a lot of scope for research for students in the country. There are many universities are also contributing in this fusion research, and the Department of Atomic Energy is also contributing in a big way, both in terms of producing the materials, the different systems, and that of course in the government of India is contributing by way of cash. So what I wanted to share with you today, that while the nuclear fission has been already utilized for producing electricity in our nuclear reactors, the nuclear fusion is yet to be realized for producing electricity. But maybe you young students will see one day that we are producing electricity from the fusion power, and so the challenge, it is a challenge for all the students to participate in such big mega projects, those who are in the field of nuclear chemistry or nuclear physics, or even in fact many engineering students, mechanical engineers, all types of disciplines are involved in producing this kind of a facility. So I will stop here, and the next I will take in the next lecture the production of radioisotopes using different types of nuclear reactions. Thank you very much.